Welcome. I want to talk today a little bit about inverse problems. They are everywhere in mathematics. And here I have kind of a brag a little bit with my own work on this fascinating part of mathematics. Actually started one of my first articles was written with my wife and astronomer on wind tomography, which works. These are typical inverse problems that you have data and you want to actually find a model or a random Jacobi operators. It's something which I worked on for some time. This is a book about this. It's a very fascinating topic. You have the spectra of some random operator. You want to find what type of dynamical system is there, or what is the isospectral set, and also scattering theory is a typical case that's related. You have some asymptotic data and you want to find out about the system or statistics. Almost all statistics are inverse problems. You have some data and you want to find the distribution, you want to find models, and you want to find the relevance of these data. And so it's everywhere. Tomography problems are very exciting and important. So you want to see inside the body, inside your knee, and you can do that with machines, with CAT scans, and so this is interesting mathematics, and it's actually quite related a little bit what we want to do today, and also the Hausdorff moment problem, which is actually a problem from statistics, also, so you know the moments of all the moments of a random variable, especially in higher dimensions, multivariate distribution. You have all the moments, and you want to find the function back. I also worked on kind of some AI related stuff. So there are whole Bibles about this. It's a huge topic. There's a lot of mathematics involved. Like, for example, the OCR problem. You see a picture and you want to find the letters. And so I've actually kind of from scratch here started once a project in the summer 2001. Could not finish it because the summer was too short, but it's a very interesting problem. So you have a text, and first of all you have to arrange it so that you know where the lines are, then you have to figure out where the words are, you have to figure out what the letters are, and so on. So you have to match the letters, and I was especially interested there with a moment kind of approach, which didn't work that well. I think it's better to just to match with just a given set of characters. And also AI. I mean, we worked on some chatbots 10 years, almost 20 years ago now, and it was an interesting problem. We have quite interesting things discovered there, and also which I still use. For example, a machine can automatically generate problems or understand. The problem is how to understand problems. So the goal was, of course, to have a bot passing an exam, like our 21A course, pass the course. And so it's an interesting thing. Even very narrow problems can be difficult. You have to understand speech recognition, of course. That's also part of artificial intelligence. Yeah, this is kind of more a mathematical, number theoretical problem, but it's related. So you know some numbers modulo some integers, and you want to know, as a calendar problem, you want to figure out what the numbers are. The structure for motion, that was a lot of fun. Structure for motion is a big topic, and in computer vision. So what you have is, this is, for example, this is a book about this, where you have multiple views of a scene and you want to reconstruct the scene. So I was just flying with my drone a couple of miles, and the task would be, of course, then to reconstruct all the houses and the trees and everything, what you have seen, at least what you have seen. And but that problem has essentially been solved. If you look at Google Earth, that the reconstruction is done automatically from pictures. So reconstruction of construction of a model from data is a typical problem. I also kind of in geometry, that's more related here, but I want to say something about spectral problems. You want to kind of, from spectra, you want to figure out topological features of the object which you hear. And so this was kind of one of the places where I got interested in that. But today I want to just talk about two problems which came up last week, and I don't know how to solve both of them, and I also am sure that both problems can be solved. So this is maybe even very easily be solved if you have good ideas. Just want to bounce a few things how I thought about this. First of all, the first problem is extremely interested, and because we started teaching this week, so we look at level curves of a function or contour maps of a function. So I have here kind of a mystery function. Just took a function half an hour before, and I kind of plotted it, printed it out, and the task would be, how do you find the function which was used? And so that's quite an interesting. I can tell you what the function was here. It's just x to the fourth. Minus, just look up what I did. I just took something random. Minus x squared y minus y x squared. I kind of just liked the shape of these two things here, these two ears which appear here. So, but the only thing you're given is this, and from that you want to actually find that function. It's a pretty tough problem, and I tried it out with some function which we actually used for our first lecture, and of course what you can do is data fitting. So what I did is just you make a grid. You make a grid, and then from maybe I can show you the code, Mathematica code. I took maybe a dozen or 2 dozen points, and I looked up the value, and then you have data points, and you have the data points x, y, z, and from that you do basic data fitting. It's solving a system of equations the best possible way. This is a least square problem, which you learn in linear algebra, and which is also very heavily used in computer vision. So least square problems are very, and then you kind of and you use maybe a dozen possible functions. I took 1x, x squared, x cubed, y cubed, xy squared, and so on, and then you look what is the best possible fit. So this is in a high dimensional space. You look what is the best possible fit, and that actually worked pretty well. I did also a second, this morning I tried something else, that you take the picture, and what I did is just actually just sample it. So I took a picture 600 times 600 pixels, and I only gave the curve. I only was given the curves, not the shaded thing, not the, and then find the, and the contours were given in different colors. And what you do is you scan through these 600 times 600 points, and then when the point is not white, not the background, then you take this as a data point. So that gave about 20 or 30,000 points, and then you have a data fitting problem in a space, in a very high dimensional space, and that didn't work that well. I don't know why yet. Probably here it would be easier, but just maybe to pick a few random points, look what the color is, encode the color with a value, and then do do the data fitting with just a few dozen points and not with very many points. So this is a fun problem, and of course there would be other approaches. One of the things which I also tried also this morning before I came here was just kind of the machine learning approach. It's like with face recognition or so. What you do is you train the system. What you can do is you can just produce a huge number of such examples. So what you do is you give a few hundred, maybe a few hundred such plots, and then what you can do, you take your plot which you have and you try to see which one fits best, and then from there you could use some machine learning things so to actually tune the parameters, to zoom in to the right, just change the parameters so that you go with along the gradient to the best possible fit. So so it was a lot of fun to actually look at that. I did not find this problem anywhere. If you look it up, the only place I found is a kind of a that's why I call it Terra inverse problem. I found it from a military academy. I think there was a paper about this. So, but otherwise I did not find anything. Even so, I think it's a very interesting problem. It's also in general, in pure mathematics, an interesting problem. For example, you have a level surface, higher dimensional level surface, a manifold or variety, and you want actually to see what function generated that. If it's a hypersurface, this is an interesting problem, and related to many other questions which you routinely look at in mathematics. Like for example, some projections, and you want to find out what the function is, or this is Fourier, or you know locally what happens with the function, how it behaves, and then use a Taylor expansion to generate the whole function. So there are many problems which are related. But here, this would be actually, I think, a cool problem to do really well. So you have a text from a textbook, you take from a textbook a level surface, and the machine would give you back, oh, that was this function which was used. So that's this problem. The second problem is maybe more serious or more related to what I was thinking about more recently about these quivers. So if you have a graph, here I have a graph, blue is the graph, and I attached some loops. And I talked about this a couple of times. I think about the loops as divisor values. So we attach here 2 and we attach here 1. And so that's kind of just additional data. Now it's well known, and that's a problem from which also comes from geometry. When you want to reconstruct the geometry from the spectral data of the Laplacian, this in general doesn't work. So this inverse problem doesn't have a solution. One doesn't know it for, say, for a convex drum. For a convex drum, one doesn't know it yet. The counterexamples are not convex. But so also in graph theory, one has studied that. But there are many graphs which are isospectral, but they are not isomorphic graphs. But you can ask, what happens if you also know more spectra? Also the spectra, say, if I attach a loop here, you have the spectra, or you attach additionally 2 loops here. And I'm confident that you can answer the question if you know all these possible spectra. The question is, how much more additional data do you really need? But the idea would be that you have this kind of quiver or this molecule, and you are allowed also to excite nodes with additional loops, and you can hear also this. I can hear that molecule. I can hear the molecule when I attach one more. Right? You can actually kind of say, okay, I want to actually hear. Additionally, I want to have another loop here, and now I know also this spectrum here. And if you know all this spectra, I'm sure you can reconstruct the graph, but I don't know how. And so I worked on this a little bit, thought about this a little bit. Maybe I just tell what I know, thinking about it for a while. First of all, you can look what happens asymptotically if you take one point here, like here, and I go with the number of loops here to infinity. What happens is essentially, what happens then here with the Kirchhoff matrix, you just add, for example, you would add here, instead of 2, you would add 2, you would have 200 here. What would happen if you have the 200 here? Of course, that will kind of dominate in the end when you, especially if you start making all of the diagonal elements larger and larger, you get kind of an asymptotic. And the question is, can you from this asymptotic then get back the graph? I'm sure yes, because what one can relatively easily get is the degrees. So you just look how the maximal eigenvalue, you know, you take here that, and you look how the maximal eigenvalue grows. And that growth rate, you know, that kind of asymptotic linear function, this is kind of like a scattering problem. So that was kind of one of the things I got only tangentially interested in this, some spectral problems in Schrödinger operators, but so this is a huge, I think that's the Bible of scattering theory, Reed and Simon, and so there are lots of interesting mathematics is involved, and that's kind of a scattering problem. Scattering. So if you take this data, if you take this number of this excitement energies, you go to infinity and you want to kind of, you know all the data, and from this you should be able to get back the geometry, but I don't know how. So I'm also sure that it's possible, would I make any bet that it's possible to do that from all the data, because there is some, there is also some, if you kind of be a little bit even more, you give even more data, and you don't ask this to be integers, but you ask this to be real numbers, then you have even more data, and you can use some perturbation theory. So what you know, of course, when you know the spectra, and when you know for all x, you know the spectra, you know how the eigenvalues change. And from the rate of the eigenvalue change, that's the Adamar first variation formula, which is, I think I showed that a couple of weeks ago. Kind of, this is very simple. I mean, you can do that. Also this, you can immediately just start with a k u is lambda u, and you start differentiating and so on, and you get this. These are the eigenvectors, normalized eigenvectors, which have length 1, norm 1, and then you have that the rate of change. With the rate of change, you get the eigenvector, the absolute value of the eigenvector. That's not yet enough, because you wouldn't, if you have all the eigenvectors, you could reconstruct the matrix, of course, just by you know then the matrix which diagonalizes. You know the diagonal matrix, you know the matrix which diagonalizes it, so you know also the original matrix. But we know only the absolute value. That's why I'm not yet. No, we only know the absolute value. Then you can try to have take higher derivatives. That's a famous formula, the Hadamard, the second variation formula, which is actually involves here derivatives of these are derivatives of the eigenvalues, and this kind of shows that if the eigenvalues are close together, they are there. This is eigenvalue repair. This is kind of like the acceleration. So if they get close together, they move very, very fast. They get accelerated very fast. It's like particles moving. But also this doesn't give you more information here. It doesn't give you information about the sign of the UJs. But I'm sure you can also get the signs somehow. But I don't yet know why, and why this is possible. How you can do that. So it's an interesting problem, and you can generalize the problem, of course. You have a self-adjoint matrix or symmetric matrix, maybe integer matrix if you like, and you look at you're allowed to add diagonal elements, and for every of these diagonal elements, you know the eigenvalues, and from this you should be able to reconstruct the matrix, the original matrix. Also, I'm sure here that this is possible. Maybe this has been done already somewhere. I could not find anything about this, but it's an interesting question. Okay, so that's it for today.